Hey everyone, welcome to Kris Studio. I'm your host Kris with K. Today I wanted to talk about stress strain curve a little bit in this video. So here's a graph, we call this stress strain curve, and it says strain on the bottom and stress on the vertical axis. Stress is the force divided by the area, and the strain means how far the material is moved. Let's see the curve. If we are pulling steel bar, we will get the SS curve like this one. So if we start yanking the steel bar, what's happening in the material? The steel bar will deform a little bit when we start pulling, and the stress and strain is rising like this. But at some point, we don't yank the steel bar anymore. What's happening there? Well, the steel bar is turning back to its original shape. It means the steel bar deformed a little bit when we apply force to it. But it cannot detect any change because the amount of deformation was too small, right? Furthermore, the deformations disappear when we stop yanking. So it is called often elastic. We've stressed to the material, so the stress has gone up, but it is not gone past its yield point. So in elastic condition, there's no deformation, no change, nothing happened to the material, right? How about this B to E? It's gone past its yield point. And what's happening to the steel bar? If we take the steel bar and stretch it, it might be elongated than its original length. Or if we flex the steel bar, it cannot snap back to its original shape. So this one B to E, we are in the region called the plastic region. In this zone, it gives deformation to the material, and the material changes its shape permanently, right? Now, the external force or stress rose steadily, and it stands on point C. It goes its highest stress level. So we are at the point called the ultimate tensile strength or maximum tensile strength. That if we keep pulling the material more and more, stress goes through the UTS. So what would happen there? There the stress goes down and down without striking any bottom. Even as the decrement, there's something interesting happens. When we are in the plastic region, the material elongated uniformly until reaching the UTS. But if the stress goes through the maximum tensile strength, the deformation is going to progress at a specific part of the material. It could be surface defects, or it could be the decarburization, or it could be a tiny crack. That the deformation is accelerating the weak zone of the material. Say it another way, the other sides of the material do not elongate it than the specific point. The stress has just concentrated on the specific part. So the concentrated area is decreasing when stress has gone up, and finally the material would just break all of a sudden. So this is a common SS curve for the ductile materials. Most of the commercial materials, especially steel, show this tendency. But some materials like multi-synthetic steel or glass don't have like this behavior. Alright, let's do some examples. The blue one looks similar to previous SS curve, right? Straight line means the particular status, which the material can go back to its original shape. Then the rising curve, we are in the region called the plastic region, right? And what happened in this region? The material cannot be returning to its original shape, and finally it breaks. This curve shows typical SS curve for ductile material, and you can see each stage of the tensile test. Well, the first one, what it is on the elastic region, and this one is elongated than the first one, right? So we can say it is within the plastic region. How about third? It goes through the necking point. It means no more uniform deformation to the material. The stress concentration begins in this stage, and it comes to the fourth one. And finally, we can easily know its destination. Let's go back previous curve. The blue one shows typical behavior of the ductile material. And then you just focus on this point. What happened? The fracture occurs in the smallest area of the material. In other words, the stress concentration became in this region, right? What about the red one? It looks similar in shape to a blue curve. It also has the elastic region, right? The odd thing was that we cannot find any plastic region in this one. Actually, it has also plastic zone, but there's a tiny amount of plastic deformation, and then it breaks right away. In comparison, the blue one, a ductile material, was accompanied by enough plastic deformation that you can recognize, but there's not enough plastic deformation in red one. It means that the breakage will happen all of a sudden. This is characteristic of martensitic steel, and it's also characteristic of brutal material like glass. So in this video, we just took a look for the behavior of the ductile material and brittle material in tensile test. Next time, we will discuss some examples of the SS curve. Thank you for watching.